Hi, I'm Tom Beebekauser with Wetland Restoration and Training. Thanks for joining us today. Today we're going to be talking about how to build a spillway for a wetland. Well, what's a spillway? Well, we're looking at one right here. A spillway is the pathway that water takes when it's overflowing out of a wetland. And it's really important that this be built correctly because if there's erosion in a spillway, it can work its way into the wetland and cause the destruction of the wetland. So we're going to be looking at how do you build a spillway where the water spreads out and doesn't cause erosion. And if you do it right, you can turn your spillway into a wet meadow wetland, which is a real bonus. So let's get started. We're looking at the spillway for a constructed wetland, and you see the way it's built is that it's very wide and the water flows over the ground in a sheet-like pattern. And when it flows over the ground that wide, it saturates the soil and it ends up making a wet meadow wetland. And there's absolutely no erosion. This wetland was built 17 years ago. The wetland looks great, the spillway looks great, and we have quite a bit of wetland habitat here. Here's where water flows off a football field at the Rowan County High School in Moorhead, Kentucky. The water coming out of the culverts flows over the rock that's embedded in the ground and then enters a wetland that we constructed using the compacted clay liner technique. This is the inlet for the wetland. A spillway is the path that water follows when flowing out of a wetland. People also call a spillway an overflow or an outlet. The arrow shows the spillway and the direction water is flowing out of the wetland. Every wetland that you build is going to have a low edge, and when there's a flood, water is going to pour out that low edge of where you built it. Now, if you built a dam, you need a spillway. You don't want water going over the dam. It'll cause tremendous erosion. Here's what happens when you build a dam and you don't have an adequate spillway. It starts cutting a channel, you get head cuts forming, and pretty soon you have a torrent of water coming over that edge. And the head cuts will advance into the wetland pool and drain your entire wetland. This is why you need a well-designed and built spillway, so you don't have erosion. During a storm, water quickly fills the wetland, and then it begins flowing out the spillway that we constructed. Water entering the wide spillway quickly spreads out in a sheet-like pattern. This spillway is about 20 feet wide and it's level in cross-section. It was built on only a 1% slope. There is no defined stream channel in the spillway. The soil in the spillway is saturated and the spillway has become a wet meadow wetland. This wet meadow wetland supports a diversity of flowering plants that are used by pollinators. The arrow shows another spillway for a wetland. One can locate the spillway by walking around the wetland and looking for where water is flowing out of the wetland. The spillway often looks like a bay or an extension of the wetland. One can watch for a flow of water to see where water is leaving the wetland. Sometimes it's necessary to place leaves in the spillway or to muddy up the water with your foot to see where water is flowing out of the wetland. A spillway is also a stream, and like a stream that's not eroding, it has a wide channel with low banks and it flows over a gradual slope. This spillway connects two newly constructed wetlands on the Monongahela National Forest in West Virginia. Constructed wetlands can last for hundreds of years if they have spillways that are not eroding. The spillway in this photo connects two newly constructed wetlands on the Monongahela National Forest in West Virginia. The spillway is wide, it has low banks, and flows over a gradual slope. Every wetland must have a spillway, including large wetlands like this one, and very small wetlands like this one. This drawing shows where a spillway can be located on a wetland constructed with a dam. The spillway can be placed on one end of the dam or the other. The spillway will move water around and away from the dam because water flowing over the dam will wash out the dam. This drawing shows where a spillway can be located for a wetland that is built without a dam. Water is flowing out of the wetland at the lowest point along the edge of the wetland that was built. The spillway should be built to have a slope of 1% or less. This means that there should be no more than a 1 foot change in elevation for every 100 foot length of stream that is built for the spillway. This map with 1 foot contours shows where we'd like to build a couple of wetlands. The 1 foot contours are shown in blue. I've outlined in red where it's possible to build two wetlands that would have no more than a 2 foot change in elevation from upper to lower edge. These yellow lines show where dams would be built to make the wetlands. The green color lines show where spillways should be built for each wetland. The spillways would be built on slopes less than 1%, and each spillway would end in a drainage that is fully vegetated with no head cuts or erosion. Spillways that are built with a slope steeper than 1% should be armored with rock that is embedded into the ground to control erosion. Rock that is angular or fractured should be used when armoring a spillway. Fractured rock can be compacted so it fits tightly together, just like the pieces of a puzzle. The rock should be mixed in size from 6 to 12 inches in diameter. Avoid using round rock because it cannot be locked together. This drawing shows what not to do when using rock to armor a spillway. The rock was placed on the surface in a thin layer and it was not embedded in the ground. The rock will be washed downstream when it rains. There are wide spaces between the rocks. Water flowing in this spillway will flow around the rocks and it will cause erosion. The rock used in this spillway is also bad news. The person building this wetland tried to save money by spreading a thin layer of rock in the spillway. The rock they placed is barely pushed into the ground. See how the rock sticks up high from the surface? Water flowing in the spillway will be deflected when it goes around the rocks that are sticking up on the surface, and there will be erosion. Now this is how rock should be used to armor a spillway. The rock is embedded in the ground so only the tops of the rocks are visible on the surface of the spillway. The rocks are compacted to fit tightly together to form a layer that is at least 12 inches thick. I recommend spreading a thin layer of soil to the surface of the rocks and then using the excavator to push this soil into the spaces between the rocks. Action must be taken to make sure that the downhill end of the spillway does not erode. This drawing shows how we used rock to armor the slope leading into a ditch at the end of the spillway so head cuts wouldn't form. A head cut that starts at the end of a spillway will advance up the spillway and eventually destroy the wetland that is built. The spillway should be built to be at least 12 foot wide with gradual sloping banks so water can spread out during a flood. I've built spillways that are more than 30 feet wide where streams enter a wetland. The spillway should be built to be level in cross-section with a slight dip in the center so water doesn't cut a channel along one edge of the spillway. Water flowing in a newly constructed spillway can erode deep gullies along the toe of the banks unless a shallow dip is placed in the center of the spillway and the banks are made with gradual slopes. We're going to look at what happens when a poor job is done building a spillway for a wetland. This is a constructed pond on a ranch in Arizona. We can tell that the pond sometimes holds water because willows are growing around the edge and the basin has exposed soil. We walked around the dry pond to find the spillway. Water leaving the pond had formed a ditch in the spillway. Before the pond was built, there was no eroding stream channel because water flowed over the surface in a sheet-like pattern and there was no erosion. We decided to inspect the path of the spillway to see if action could be taken to control erosion that is possibly impacting a rare species of fish downstream. Within a few steps downhill, we found head cuts in the spillway. The head cuts were causing a deepening and a widening of the stream that was flowing out of the pond. The head cuts were moving uphill towards the pond and would soon enter the basin and drain the pond forever. Water flowing out of the pond had eroded a gully. Just downhill of the gully, we found this head cut in the spillway that was causing erosion. As we walked downhill, the spillway changed from a gully into a canyon. Water flowing in the spillway from the small tributaries was causing additional head cuts to form. Where the hillside was steeper, the head cuts became deeper and wider. The spillway was actively eroding as one could see roots sticking out of the vertical banks in the side of the channel. It's hard to believe that the simple action of neglecting to build a spillway on a gradual slope that was armored with rock could cause this canyon to form downstream of the pond that was built. Water in the spillway eventually dropped into the stream, and the stream was also eroding. The spillway constructed for this pond was narrow and it dumped water on a steep 10% slope that was not armored with rock. The dam built for the pond had blocked a large watershed, and the spillway carried overflow over highly erodible sandy loam texture soil. Unfortunately, the sediment that's being carried downstream enters the river with a federally endangered fish species. It would be extremely expensive to repair this spillway and to try to stop the erosion. Let's look at what happened when an inadequate spillway was built for a pond in southern Arizona. This pond is called the Geronimo Pond. The Geronimo Pond was built in 1956 on the Coronado National Forest in Arizona, and it's near the border with Mexico. The pond does not hold water. The Geronimo Pond was built using a dozer that constructed a 20-foot-high dam across a valley that had a very large watershed. A spillway had been constructed for the pond where the dam ended at one side of the valley. The spillway was built narrow and it dumped overflow down a steep slope. The infrequent but torrential rains in the desert sent water rushing down the valley. The runoff quickly filled the pond. The pond then overflowed the dam because the spillway was too narrow and it was too high in elevation. The water flowing over the dam and the spillway cut a deep channel down the mountainside and then into the basin of the pond. Head cuts formed in the spillway that rapidly raced upstream. The head cuts cut a deep gully in the pond basin and drained the pond. The flow of water in the failed spillway caused head cuts with a 7-foot-high vertical face to form. The shear stresses were so high that large boulders cascaded down the mountain with each storm. The eroding spillway would be nearly impossible and very expensive to repair. To repair the pond, it would be better to build a new spillway where you see the pink ribbons. This is where the dam ends at the other side of the valley. The spillway would carry water away from the dam and down a slope less than 1% to control erosion. To build the new spillway, it will be necessary to dig 7.4 feet deep through a narrow ridge where the end of the dam ties into the high side of the valley. We examined this ridge for the presence of bedrock to make sure it would be possible to dig through the ridge without the need for a whole ram attachment on the excavator. The new spillway must be at least 12 foot wide and have gradual side slopes. The entrance to the new spillway should be at least 2 feet lower than the top of the dam. The downhill edge of the spillway must have a bank high enough to prevent water from flowing over the side of the spillway and causing erosion. An excavator with an operator will be needed to cut through the ridge to build the new spillway. A dozer and an operator will be needed to build the new spillway and to repair the dam. The soil removed from digging the new spillway will be used to build a section of dam that blocks the old washed-out spillway and raises the elevation of low places in the dam. The dam will be built to resemble a natural ridge that is high enough so that water will not flow over it during a flood. One source of soil that can be used to rebuild the dam is the large amount of sediment that's deposited at the inlet to the dry pond. Another source of soil that will be used to repair the dam will be the soil and rock removed from building the new spillway. We can obtain even more soil to repair the dam by removing soil from within the dry pond to form a deep basin where an aquatic safe liner can be installed. The rebuilt dam will be made level with a top at least 12 feet wide. The slopes on the inside and the backside of the dam will be gradual, averaging 10%. Trees and shrubs growing on portions of the dam that are more than 2 foot higher than the spillway will not be removed. The center location of the new spillway was marked in the ground using pink-colored plastic ribbons and pink-colored wire flags. The new spillway would be built about 14 feet wide. Wire flags were used to mark the location and the elevation of the spillway, with additional flags being used to mark the end of the spillway. The flags were placed to mark the center of the spillway to build. The spillway would be built so that water would flow in a wide path at one elevation, so no rock would be needed to control erosion. The spillway would be dug so that it's level along its length and there will be no erosion. The entrance and the exit of the spillway would be at the same elevation. Let's visit the Brown Canyon Ranch on the Coronado National Forest in Arizona. This is where we built 2 wetlands using aquatic safe liners that were buried in the ground. Here's the wetland located uphill. We call this the Brown Canyon Ranch Pond. Here's the lower wetland. We call this the Wild Duck Pond. Both wetlands provide breeding habitat for the federally threatened Chiricahua leopard frog. The wetlands are supplied with water from a spring. A pipe carries the water from the spring high in the mountains to the Brown Canyon Ranch Pond in the valley. Because there is almost always water flowing out of the Brown Canyon Ranch Pond downhill into the Wild Duck Pond, we built a spillway that was 12 foot wide and level in cross-section to handle the overflow from one wetland into the other wetland. The spillway from the Brown Canyon Ranch Pond carries water over a gradual 1% slope into the Wild Duck Pond. The soil along the path of the spillway is saturated with water. This creates conditions for wet meadow wetland to develop. Here's where the spillway from the Brown Canyon Ranch Pond enters the Wild Duck Pond. The spillway we constructed has become a unique wet meadow wetland in the desert. A bonus is that the wet meadow created in the spillway now provides habitat for Chiricahua leopard frog juveniles. These young frogs could be eaten if they stayed in the deeper water that's found in the wetlands where the adult frogs live. I helped build a fishing pond that was 1.3 acres in size in the desert of western Nevada. We also built a stream that was 200 feet long and a small wetland that was 60 feet in diameter. Here's how the small wetland appeared the day it was finished and before it was filled with water. We used aquatic safe liners that were covered with thick layers of soil to build the fishing pond, the wetland, and the stream. We used the liners because the texture of the soil was low in clay and the groundwater was way below the surface. The stream, fishing pond, and the wetland are kept filled with water from an 8-inch diameter well that was being used for irrigation. The stream we built is the water inlet for the fishing pond and for the wetland. The water from the stream eventually flows out of the fishing pond. We built a spillway that is 30 feet wide and 1,160 feet long that is supplied with water flowing out of the fishing pond. The spillway was built so water would soak into the ground and it would become a wet meadow wetland. One of the first steps in building the spillway was to decide where the spillway would begin and where the spillway would end. We selected undisturbed ground at one end of the dam that was built for the fishing pond to be where water would enter the spillway. We purchased rock for armoring the entrance of the spillway. The rock armoring at the entrance of the spillway was needed to protect the area from being rutted by motor vehicles that were driving around the fishing pond. This traffic had the potential of lowering the elevation of water in the fishing pond by lowering the elevation at the entrance of the spillway. We wanted to build a spillway as long and as wide as possible to create wet meadow habitat. While on the ground examining the area where the spillway would be built, we identified a drainage along the eastern edge of the property, and this drainage was not eroding. This drainage would allow us to move water downhill from where the spillway would end into the river valley below without causing erosion. To identify a path for the spillway, we used a laser level to take elevations in the area between the entrance of the spillway and the eastern edge of the property where the drainage was located. Because of the thick and the tall plants, we set up a tripod and a laser level in the back of a truck so it would be high enough to clear the vegetation. We used the laser level to record elevations so we could mark a path for the spillway that changed only 6 inches from the entrance to the exit of the spillway. To build the spillway, it was necessary to dig a 30-foot wide channel that was only 4 inches deep in the center along its entire length. We tied colored plastic ribbons to the shrubs to show where vegetation should be removed to build the spillway. After the excavator removed the vegetation, I used a laser, tape measure, and wire flags to mark both the upper edge and the lower edge of the spillway we wanted to build. We used a marker and wire flags to mark the elevation of the spillway that we're building along the entire length. The center of the spillway was dug so it was 4 inches lower than the elevation of undisturbed ground along the downhill edge of the spillway being built. This created a shallow channel so that water in the spillway would not overtop the banks and cause gullies to form by taking a shortcut downhill. We did not build a dam or a berm along the lower edge of the spillway. Don Smith, the excavator operator, shaped the spillway to be level in cross-section with a shallow dip in the center that was 4 inches lower than the downhill edge of the spillway that was being built. We spread the soil that was removed beyond the lower edge of the spillway being built. The soil was spread and fanned out. It was not shaped into a berm. The uphill edge of the spillway was sloped, so there would be no ridge or berm that prevented runoff from entering the spillway. Don Smith used the teeth on the bucket of the excavator to loosen and to rake the spillway to a depth of 12 inches so that water would soak into the ground. There was no need to armor the spillway with rock because it was built with a slope of less than 1/10 of 1%. We did not use the rough and loosen technique in the spillway because the pits and mounds could concentrate the flow of water into narrow channels and cause erosion. We did not place logs or piles of brush in the spillway because these could concentrate a flow of water and also cause erosion. We asked the people managing the ranch not to drive motor vehicles in the spillway because that could leave ruts that would concentrate the flow of water and cause erosion. The spillway has become a wet meadow wetland that provides habitat for the sage-grouse and for a diversity of pollinator species. I helped volunteers with the Dallas Barnhart Vale Nature Park Restoration Committee to design and build wetlands in the community of Barnhart Vale in British Columbia, Canada. Barnhart Vale is in the southern interior of British Columbia, and this is where wetlands are like jewels on the landscape. We worked together to identify places to build wetlands at the Dallas Barnhart Vale Nature Park. We designed wetlands to be built on a mountainside where water from springs had saturated the soil. The use of the laser level showed us that the ground was steep, with slopes varying from 6 to 9%. We designed the wetlands to be stair-step down the slope. Each area we marked in the ground would have from a 3 to a 4-foot change in elevation from upper to lower edge. We marked the perimeter of each wetland we wanted to build with colored plastic flagging. It's a real challenge designing wetlands in arid regions where springs are located. This is because of the dense growth of shrubs and trees. It's difficult to survey and to look for ditches where vegetation is growing this thick. We used a 2.5-inch diameter open-face clay auger to dig test holes at each area where we were going to design a wetland. The texture of soil near the surface was silt loam, and there was sand below the silt loam. Groundwater entered each test hole that we dug, and there were often small puddles of water on the surface of the ground. We found pipes buried in the ground in almost every wetland that we designed. The wells, well covers, and the pipes showed us that ranchers had been drawing water from the springs over many years. We found plastic pipes for moving water and clay tiles for drainage, all of this while designing the wetlands. I should have known we would need to armor with rock the inlets and the spillways for the wetlands we wanted to build. This is because of the steep slopes, the sandy texture soil, and how fast water enters each test hole that we dug. The group hired Tim Hall to provide and operate the excavator that was needed to build the wetlands. We began construction by using an excavator to dig a test hole near the center of each wetland we wanted to build. The sand content increased the deeper we dug, and as we watched, water would quickly fill the holes that were dug with the excavator. We planned to build each wetland using the groundwater technique, and this technique is described in episode 13 of this How to Build a Wetland series. Tim Hall used the excavator to remove the trees and shrubs within the marked perimeter of the wetland we were building. He saved this woody debris for later placement in and around the finished wetland. Because one generally moves an excavator backwards when digging, Tim drove forward into the far edge of the wetland we were building, and then he worked his way out backwards while digging. This is much like what you do when you're washing the kitchen floor. It was necessary to dig a trench for a groundwater dam around the lower perimeter of each wetland we built. This is because there were pipes buried in the ground. You can see a piece of clay drain tile removed when digging the trench for one of the groundwater dams. Tim Hall is using the bucket on the excavator to compact soil that is placed in the core trench to form a groundwater dam. Clay texture soil was not available, so we placed topsoil mixed with silt loam in each core trench. The groundwater dam will help keep water in the wetlands by controlling water losses via the pipes buried in the ground and through sandy layers of soil beneath the surface. Tim is digging the wetland to be deepest in the middle with gradual inside slopes. Water is filling the basin as he's digging. Here you can see why it's important to use a large excavator to build wetlands when using the groundwater technique. This excavator that weighs over 40,000 pounds can stay on dry and firm ground and then reach into the saturated soil to dig the wetland without getting stuck. It would not have been possible for a smaller excavator to build these wetlands. This shallow wetland is almost done. Tim is spreading the soil removed from digging the basin. Okay, here we're having trouble because the excavator has started sinking into the mud. Tim had to find some logs to place under the tracks to keep him afloat. Tim moves the excavator up on the logs, much like getting on a raft. He can use the excavator to dig in saturated soil and not get stuck when perched on top of the logs. We were happy to see that the wetlands were filling with water, happy enough to dance in the muddy basins. But I thought we broke water pipes the way water rushed into some of the wetlands. What happened is that we had cut into permeable sand layers, and these were carrying water underground in streams. Our celebration ended when we saw what was happening after the wetlands filled. We built the wetlands on a steep slope with water flowing from upper wetlands downhill into the lower wetlands. The water flowing out of the upper wetlands quickly caused head cuts to form in the spillway. Because of the sandy soil, the head cuts were carving gullies down the center of each spillway. These head cuts were advancing uphill into the newly dug wetland basin, and they were in danger of draining the new wetlands. Water was cutting channels through the narrow dams that we had built, and these were also draining the wetlands. I have learned since not to build dams, but rather to excavate depressions to avoid this problem. We also observed that water entering the new wetlands from beneath the surface of the ground was cutting deep channels in the wetland inlets. The water entering the wetlands first caused rills and then gullies to form. This erosion was filling the new wetlands with soil. We needed rock to armor the spillways, and we needed rock fast. This was a problem. We had not budgeted for buying rock, and neither had we let a local quarry know we needed rock, or the dump truck drivers who would deliver the rock. Volunteer Cliff Tolles and Tim Hall came to our rescue. They contacted a local quarry to order the rock, and they found a dump truck and a driver that could begin delivering the rock. But there was another problem. The dump truck driver had to unload the rock at the end of the road so he would not get stuck in the mud closer to the wetlands. Cliff Tolles rushed home and brought back a small wheel loader. We call this machine a bobcat, and we use this to move the rock to each wetland inlet and spillway. See how this rock is rounded? This is called river rock. It's best to use angular or fractured rock to armor a spillway. This is because they fit tightly together when pushed into the ground. Unfortunately, the quarry did not have angular rock, so I was happy to get the rounded rock. We had to cut down small trees and place them in the ground where there was a danger of the bobcat getting stuck. This practice of lining the ground with trees to make a stream crossing is called making a corduroy road. Cliff moves the rock to the spillways that he can access without getting stuck in the bobcat. The bobcat can move the rock faster and for less money compared to using an excavator. This allowed us to keep up with the excavator that was building wetlands. Cliff was able to dump the rock in the spillway, but the ground was too soft for him to spread the rock without getting stuck. We had to rake much of the rock into position by hand. The rock had to be placed in the channel and up the sides of the spillway. It was also necessary to place much of the rock by hand. We would walk over the rock and stomp it into the ground. Tim Hall also placed rock using the excavator. Here Tim Hall is rebuilding a groundwater dam that washed out before the rock was delivered. He rebuilt the groundwater dam using loam texture soil because this soil was the least permeable that was available. Tim uses the bucket and the excavator to compact the soil in the groundwater dam. Elevations are taken often with the laser level to make sure that the entrance to the spillway is not too low so it drains the wetland, or it's too high so water does not flow over the spillway. When taking elevations, allow for the thickness of the rock that will later be placed in the spillway. Tim placed a layer of fine limestone dust from the quarry over the top of the groundwater dam to serve as a base for the rock. The fine limestone will harden like a well-traveled gravel road. He now spreads rock over the surface of the groundwater dam. This is so it won't erode. The elevation of the groundwater dam will be the same as the original surface of the ground before the wetland was built. The rock is placed so there's a gradual slope with no drop-offs, no nick points, anything that would cause head cuts to form. The rock is spread up the slopes of the spillway and pushed into the ground using the bucket of the excavator. Soil is placed over and along the upper edge of the rock spillway and then shaped to form gradual banks on either side of the spillway. The spillway is really a stream. A gradual slope is shaped where the spillway enters the wetland, so there will be no drop-off that would cause a head cut to form. Rock is used to armor the spillway on the slope extending under the water in the new wetland. This is done to make sure that water entering the wetland will not cause erosion should the level of water drop in the wetland. You can see how much rock we use to protect the inlet and the spillway of this wetland from erosion. Very few people like the appearance of rock that's used to control erosion on a wetland project. To help hide the rock, I recommend spreading soil between the rocks and spreading a thin layer of soil over the top of the rocks so that plants will grow. The dedicated volunteers sowed seeds from native plants, they planted native plants, and they added large woody debris and then mulched the spillways and the soil surrounding the wetlands with straw to control erosion. Here's how one of the wetlands appeared the day it was built. You can see 3 of the new wetlands we built on this slope. The ridges between the wetlands are original ground, not constructed dams. When building wetlands that will be supplied with water from a spring, expect the flow of water in the completed wetlands to exceed your expectations. This drawing shows water flowing in a sandy underground layer before a wetland is built. Notice that there is a typical layer of loam and silt loam soil on the surface. The groundwater is under pressure and tries to flow to the surface, but the silt loam on the surface acts like a lid to keep the water in the ground. When you excavate to build a wetland, you remove the silt loam that's keeping a lid on the groundwater. Once the silt loam is removed, the water in the ground will rise to the surface. This is much like what happens when you dig a test hole in the ground. Let's see how the wetlands appear less than 1 year after construction. The wetlands are full of water and the plants are growing between the rocks. Mallards were loafing on the root masses we placed in the wetlands. Volunteers had planted cattails in the new wetlands. I have found that cattails can spread and dominate the vegetation in new wetlands unless they're controlled for at least 2 years after construction. We used a large quantity of rock to armor this inlet for the wetland that's on a steep slope. The rock will soon be hidden by vegetation. Algae was growing in several of the new wetlands. Algae is eaten by the larvae of frogs and supports a diversity of insects that in turn are eaten by salamander larvae. It's common to see algae growing in wetlands that are supplied with water from springs. This was the main access road leading into the project area. The vegetation that was seeded and planted is growing very well. This is the smallest wetland that we built for the project. Each wetland appeared unique. There were many dragonflies laying eggs in the water. I hope to visit my friends in Barnhart Vale again so we can see how the wetlands appear 10 years after construction. The Big Ranch is owned and managed by the Nature Trust of British Columbia. The Big Ranch is located near the community of Sparwood. Over 300 elk, white-tailed deer, and mule deer winter on the property each year. In 2014, the Nature Trust asked for my help designing wetlands on the Big Ranch. I examined the Big Ranch for places to build wetlands, and I found mountains that were rocky, and there was no clay, and there was no groundwater. We were fortunate to identify one area where wetlands could be built. It was in a meadow near the Lower Elk Valley Road. This meadow was bisected by a deep ditch. The ditch had been dug to channel and to move Nordstrom Creek in order to dry the meadow. The Nature Trust was not interested in restoring Nordstrom Creek where it had been ditched, so we focused on designing 4 wetlands that could be built in 2015. The test holes I dug using a 4-foot-long soil auger, they showed that the texture of soil on either side of the ditch was primarily silt, loam, and silt loam. I could only make a thin ribbon that was 1 inch long between my thumb and my forefinger. Here I am with Rob Neal with the Nature Trust, who directed the wetland project at the Big Ranch. Rob died in 2023. It's very important to determine the texture of soil when you're designing a spillway for a wetland. This will help you decide how much rock is needed to protect the spillway from erosion. So in looking at these samples here, Here's clay. Notice I was able to make a 6-inch long thin ribbon from clay texture soil. But here is silt. My long thin ribbon is only 1 inch. That's pretty short. And then here is sand. I was not able to make a ribbon out of sand. What does that mean for building a spillway? We're going to need quite a bit of rock to armor the spillway when building out of silt or building out of sand. And if you build your spillway on a gradual slope out of clay, you won't need much rock. The presence of silt should be a huge warning sign to anyone wanting to build a wetland. Silt does not have enough clay to compact or hold water. Silt is highly erodible, so a stream flowing over silt is likely to cause major head cuts and serious erosion. Look at how this stream is cut through a high bank along the Columbia River. The bank is made out of silt texture soil. Silt dissolves like water flowing through a container of dry flour. Another problem I have found with silt, it usually overlays rock and gravel that's dry with no groundwater. The rock and gravel will drain wetlands just like the hole in the bottom of a flower pot. The day of construction, I dug a deep test hole in one of the planned wetlands and found that silt overlaid rock and gravel, and there was no groundwater in the gravel. In excavating basins for the wetlands, we would cut through the silt and expose the dry gravel beneath. We agreed to use the compacted clay liner technique to build the wetlands, only using the silt texture soil because there is no clay in the meadow. We tried everything we could think of to compact the silty soils. This included mixing water with the dry soil and using a large wheel loader with rubber tires to compact the silt in layers. We found it was not possible to compact the silt to form an impermeable layer. I thought the wetlands would hold water even with the silt because there was so much water flowing in the ditch. We built wide spillways over gradual slopes to move water from the ditch into and between the wetlands. Once the spillways and the wetland basins were built, we moved the ditch to begin supplying the wetlands with water. They filled overnight. Then we saw a big problem. The stream was cutting gullies around the edge of the wetlands and in the spillways. The silt was dissolving and washing away just like flour. It was not possible to make the water in the spillways spread in a sheet-like pattern so there would be no erosion. There was an urgent need to purchase rock to armor the spillways or the new project would be destroyed. After much discussion about where the money would come from, we decided to order rock so we could armor the spillways. Fortunately, we were able to find a business that would deliver rock to the site. We found it almost impossible to push the rock into the dry, silt texture soil. We had to first loosen the surface of the ground with a bucket on the excavator, spread the rock, and then run over the rock with the tracks on the excavator, and then sprinkle soil between the rocks using the bucket on the excavator. The loosened silt was like powder that would not compact, and the wet silt became stickier than glue. We watched with great concern as soil washed away because of water flowing in the spillways. To combat this problem, we moved the excavator around to where the erosion was occurring. We added more rock, pushing this rock into the ground within the spillways by using the excavator. We also used rock to armor the inlets where water from the ditch entered each wetland to control the erosion. The rock we embedded in the ground where the water flowed into the wetlands prevented head cuts from forming in the highly erodible soil. Here's how one of the wetlands appeared the day we finished the project. The wetlands quickly filled with water. We found that many of the mounds that we had left in the wetlands dissolved and they settled once they became saturated. The wetlands we built were like what you see a beaver building. However, beaver would not have built these wetlands because there were only a few trees growing in the meadow. The wetlands we built did not involve constructing dams or installing water control structures. Here's what one of the spillways looks like 6 years after construction. The rock we embedded in the spillways is working to control erosion. Water is flowing into and out from the wetlands in a sheet-like pattern just as designed. The spillways built on slopes that are less than 2%, they're supporting a diversity of sedges and rushes. You're not able to see the rock in the spillways where we were able to push it into the ground. The stream has maintained an open channel where it flows over the steeper slopes. Here's where the armored ditch enters one of the wetlands. Here's a section of ditch where we sloped the banks and armored them with rock to control erosion. This is the most upstream wetland 6 years after construction. Here's where Nordstrom Creek enters the upstream wetland. A diversity of wetland plants are growing in and around the wetlands. The mounds we shaped in the wetlands are growing a diversity of plants. The wetlands were built with varied edges containing points, peninsulas, and bays. The wetlands were built to have different water depths. I'm happy to see that cattails have not taken over the wetlands. The wetlands appear like natural features on the landscape. This is because dams were not used in their construction. The downstream wetland has the shortest hydro period because of a thin layer of silt over gravel. This has become an ephemeral wetland. The ephemeral wetland is a wet meadow wetland during late summer and early fall. People have been telling me that the ephemeral wetland is a failure because it dries in the summer. Miranda Cross shared these photos with me. They show the wetlands we built at the Big Ranch 7 years after construction. You can see that the spillways and the inlets are not eroding. The wetlands we built appear natural. You may want to know that our design, permitting, and engineering costs were less than 10% of the total cost for construction and planting. The wetlands are growing a diversity of plants. We built the wetlands so they would not require maintenance. So many personnel and government agencies tell me that it's not possible to build a wetland that looks and functions like a natural wetland. I wish they could visit the Big Ranch. Look how the water flows in a sheet-like pattern without causing erosion over the entire surface of the spillway that we constructed for a wetland in New York. The spillway connects two newly restored wetlands and was built to carry water on a slope of only 1%. There was no need to armor the spillway with rock. The spillway has become a wet meadow wetland. Here's a problem that can get worse. The water is cutting a channel between two newly restored wetlands that we built with no dam. There is a need to widen and armor the spillway with rock to control erosion. We decided to repair the spillway by hand instead of waiting to bring in heavy equipment. We gathered rocks from the surrounding area by hand and placed them on the ground where water was flowing. We then used our feet to push the rocks into the ground. We used our weight to create a wider floodplain for the spillway. Water is now spreading out and flowing over the rock in this maintained spillway. You're looking at a dam that was built for a wetland mitigation project that was completed in Virginia. The dam is about 3 foot high and has steep side slopes. Pine trees are growing on the dam because it has not been mowed. The wetland that was created by building the dam is on the right side of the dam. The spillway for the wetland had been built in the center of the dam, not at one end of the dam like what is normally done. We observed that the spillway needed maintenance because water flowing over the spillway was washing out a section of the dam.
So it seems like they built the spillway 20 feet wide expecting water to sheet flow over this entire area, but in reality, the low spot in the spillway is right here, and we're only seeing water come through this left edge, and they didn't armor that side nearly as much.
You see any signs of erosion?
There's certainly signs of erosion and head cutting.
You would point it out to us.
We're seeing soil loss and erosion here, and you can see this honeycomb fabric structure, which was completely covered by soil at design.
The spillway is eroding because it was built narrowly and carries water over a steep slope, which is the dam. Water in the spillway was not flowing over rock, and the rock was not embedded in the ground. Katie is standing on the crest of the spillway, which is in danger of washing out and will drain the entire wetland. We decided to repair the spillway by hand instead of going through all the paperwork and the delays associated with getting a contractor on site with heavy equipment to maintain the spillway. Repairing the spillway involves picking up rocks that were dumped on high ground and moving these rocks to where erosion is occurring so that water will flow over the rock. This is like completing a puzzle where you must match the size and the shape of the rock with the surface you're trying to armor. Once the rock is set down, you must move it into position and make it lay flat against the ground. You then stomp on the rock with your feet until it is wedged into position. The rocks must fit tightly together in the bottom of the channel and up the sides of the floodplain. It's also important to remove any logs or branches that have fallen in the spillway. Make sure rocks don't stick up high, as this will cause turbulence and erosion. The rocks have been placed so the spillway looks like a ramp. The bottom of the spillway along with the banks of the spillway are now armored with rock. The crew looks for gaps and holes that can be filled with rock. Katie stomps on the rock to push them into the ground and to flatten the rocks that are sticking above the surface.
All right, so we've been working on repairing the spillway with just by hand. So we were noticing spots of erosion and some exposed soil. So and we noticed there's a pile of rock over here that wasn't really receiving any water and wasn't really doing anything, wasn't moving much. So in order to armor the part of the spillway that's receiving most of the flow, we decided to shift some of the rocks over to this main part of the spillway, so that way we could get some nice even sheet flow. We were aiming to minimize some of the high points sticking out in the rocks, trying to achieve sheet flow across this to minimize erosive force.
In summary, it's important to remember that every wetland needs a spillway, whether the wetland is natural or constructed. A poorly designed and constructed spillway will result in the eventual destruction of a wetland. In a poorly built spillway, head cuts advance up the spillway and they will drain the wetland basin. It's entirely possible to create a spillway that will also become a wet meadow wetland. This is done by building a spillway at least 12 feet wide that flows down a slope of less than 1%. The spillway may not need to be armored with rock if it's built to be wide with a sheet flow of water over a slope of less than 1%. It's very important to use rocks to armor the spillway to prevent erosion if the spillway is built on a slope steeper than 1%. The rock you use to armor a spillway should be fractured and angular, not round. The rock should be spread in a layer that is at least 12 inches thick. Make sure to armor the entire width of the floodplain and extend the rock up on the banks of the spillway so there will be no erosion during a flood. The rock must be embedded into the ground so that water does not flow under or around the rock. The rock armoring must be done along the entire length of the spillway. Act to immediately repair a spillway by hand whenever possible to control erosion. I'm standing at the entrance to the spillway and I notice that the spillway is not flowing water. The reason is that somebody has blocked the entrance to the spillway by placing soil and branches, and in so doing they've redirected the water, so now it's flowing down the access trail to this wetland area. What we need to do is to remove this debris and this soil, and then what we need to do is to get the water to spread out and to flow in a sheet pattern down this spillway so the trail is dry and the wetland is healthy again. I know it's important to build a wetland that holds water. What's equally important is that you build a spillway that carries overflow out of your wetland under flood conditions so there's no erosion. And what you've seen today is that you can build a spillway that carries water out of the wetland in a sheet-like pattern, and it's over a slope of less than 1%, and over time you'll have a wet meadow wetland develop in your spillway. I'm Tom Beebe-Kauser. I'm with Wetland Restoration and Training, and I invite you to subscribe to this video series on how to build a wetland so you won't miss any episodes, and that you press like, and thanks for joining us today.